So, first we have already looked at this, the idea of computing, and in that we are used to these kinds of computers where the basic idea remains the same, which was conceived way back in 1936 before the computers actually existed, showing that a computer essentially is a device which uses limitless memory and a scanner to scan the memory backward and forward and read it by symbol to symbol and write additional symbols to execute any computation. That is the Turing machine. Okay. The whole idea of this principle still works and it is the same one which is given for this computer. So, that is the basic idea behind the concept of any classical computer. Okay. So, the classical computer has some limitations. Even the fact you can have limitless parallel computers, they which can do really complex work, but they are basically complex Turing engines which employ multiple computing modules dealing with pieces of incoming data which are chunks of bytes, instructions, etc. But there are problems which are beyond the competence of a universal Turing machine. For example, we cannot predict whether a program will terminate, and this is the halting problem, it's a famous one. And then there is this classes of problems which have been lineated and are solvable, for example, in polynomial or exponential time, and those whose answers are checkable in polynomial time. So, these are the classes which we will be looking at. So, these are n, so if anything can be solved in n polynomials, then it is a problem which is to be looked at in this fashion. But as the, so this is an NP problem, but as these become larger and larger, it becomes more difficult. So, we will be looking into these things more and more. And we have also discussed about Moore's law before, which was given by Gordon Moore, who is the founder of Intel, co-founder of Intel, who made an implicit statement based on the fact that he saw that the number of transistors per chip essentially doubled every 18 months, and this tendency of the computer world has kept on going since the beginning of the computers for a very long time. And that is kind of very interesting, because now we are talking about switching which are at very small scales, and the current VLSI, the very small, very large scale integrated circuits, that is VLSI, can be as small as a few tenths of a micron, and even smaller actually. They have reached nanometer scales. So, the principles of quantum mechanics are going to come, and in the spirit of Feynman, the mystery associated with quantum mechanics is something which you perhaps cannot really explain, but what you can do is you can just look at it how it works, because you cannot really, in his words, we cannot make the mystery go away by explaining it. So, that is how you look at it, and this was done, this is his famous statement with respect to the double slit experiment, where interference fringes and things were found for the first time. So, in terms of quantum mechanics, the beginning, or basically the use of quantum mechanics in computers started in 1981, where this statement was made that the classical Turing machine would probably experience an exponential slowdown because of the probability issues as you become smaller. And the immediate other side of the story was that the quantum system with many particles is described by a Hilbert space whose dimensions are exponentially large in the number of particles, which means that it can be utilized for its advantages. And this statement that this has its benefits, oops, I do not know what happened, sorry. This has its benefits, were described in a conference called CLIO in this 1981. So, it's in 1981 CLIO conference, Feynman first coined the term which is quantum computer. Then David Deutsch in 1984 proposed the idea of universal quantum computer. It was quite soon that this idea was brought out, and the qubits required were the number of particles in the system. That is how it was defined, and then it went through a lot of developments, and about a decade later, Seth Lloyd talked about a standard quantum computer which can be programmed to simulate local quantum systems efficiently. So, this was one of the important statements that he was able to make, and he was able to show, he was able to take a stock of all the developments over the more than a decade by that time, and showed that quantum computers has been extended to larger classes of quantum systems. So, well, quantum mechanics essentially are systems which involve electrons, protons, neutrons, photons, quarks, neutrinos. Any of them can be our potential qubit in some sense, and it is a system of laws that describes the behavior of such objects. So, this was predicted way back then that by 2020 we will store 1 bit of data on objects of that size. I am not sure we are there yet, but we are not too far from 2020 either. So, let us see what happens. So, one of the interesting concepts of quantum mechanics is that the atom size objects behave in unusual ways because their state is generally unknown at any given point of time and changes if you try to observe it. Now, this is a very important aspect of quantum mechanics which is different from classical ones. In a classical object, whatever you have, the solution is that. In a quantum object, unless you measure it, you do not know what it is, and secondly, if you measure it, you cannot be sure that it is the same thing that you measured because the act of measurement changes it. So, there is also this principle of standardization which exists in this quantum world, and simultaneously several properties of the systems, of such systems, can be manipulated and measured simultaneously. That is one of the other advantages of this. So, anyway, these are the motivations as to how you would be going and why you would be going quantum, and we have done this in class. I am just going to reiterate here to bring you up to speed. One is that as we go smaller, to avoid wastage in time, energy, etc., because as you go smaller, the time taken to travel goes lesser. So, wastage of time is lesser, energy required in dissipation goes down, and so eventually go to quantum. So, that is a way of looking at it. The other option is that in order to be energetically most favorable, you want to act reversibly. That comes from thermodynamic principles, that gives minimum energy loss, and the biggest important point is Turing machine is not reversible, but the quantum evolution is reversible. Okay. So, a classical bit, again the other important thing which is different is a classical bit can either be 1 or 0. However, a two-state quantum system can be in an arbitrary number of superpositions. All such states can be processed at once in quantum operations, right. So, for example, this continuously the system getting tipped is an example of a superposition principle. So, while classical essentially means either one or the other in a spin system, in quantum systems it is a continuous tipping kind of a situation where in the middle, whatever you are, you can see them. So, those are our superposition states and we can use them. So, there is this concept of hidden variables in physics which have been used quite often to even talk about these superposition and in between conditions, but we need not worry about this right now. It was assumed that quantum systems essentially meant that there were lots of variables which you cannot see, and they were called hidden variables. This is one of the concepts of quantum physics or foundations of quantum mechanics. But it was found that just by thinking that there are hidden variables, you can explain quantum mechanics. That didn't work. Similarly, the quantum process also therefore will not perhaps be reduced to a Turing machine. But on the other hand, we will be discussing something called a quantum Turing machine, which will be an analog to the world of computers that we know it. Okay. So, the definition of quantum computing which we will use is manipulation of quantum mechanical systems for information processing. And so, there are two terms here. So, let us be clear, one is quantum computing and the other one is quantum computer. Please remember, they are not the same thing. It is like noun and adjective. You do not want to use a noun in place of an adjective and vice versa. A quantum computer is the noun and the computing is actually the adjective. So, the act of manipulation, or adverb actually, act of manipulation is the quantum mechanical system for information processing, that is quantum computing, whereas quantum computer is a device that processes information in a quantum mechanically coherent fashion. And so, it could perform certain types of calculation. Now, it is important to mention this, certain types of calculations. It is not that we are going to, at least at this point of time, say that for every class of calculation it will be better, but for certain parts it can be far more efficient. And this is again the example of how they look different. In bits you can either be here or there, whereas in quantum bit or qubit you could be anywhere in between, and all possibilities of these betweens exist, which is sort of not an issue for the bit case. So, interestingly, way back in 1982, Feynman essentially looked at quantum computing from a different perspective. He was not thinking in terms of a computer that can be faster or something. He basically looked at it saying that since all natural processes are at the base or at the fundamental level quantum mechanical, you can, by using quantum computing, realistically simulate quantum systems. That was his basic principle and his basic interest, being a physicist of his kind. So, that was his main idea, that you could simulate quantum systems in the most appropriate fashion once a quantum computer is here. That is his way of looking at it. The first realistic application came as late as 1994 by Shor. Peter Shor showed that it is possible to actually find the primes, or basically factorize integers into their primes in a much faster way than it is possible by any foreseeable classical computer, because there is the place where you can see an exponential speed up by using a quantum computer. So, we will do this particular problem. And the other important place right after this, which became very popular, is the Grover's algorithm, which basically searches database. Now, you might think that this speed up of this is not as much as a Shor's algorithm, but it is hugely popular because most of the problems that you have in a quantum computer finally boils down to a search problem, because in most cases what happens is you come down to a point where you would say the answer exists. Once you say an answer exists, it is essentially a search problem of finding the answer. Okay? And the best part is when you can say that there is only a single answer, and if you say that, then this is perhaps the most important problem, the most important algorithm that you need to use, and therefore Grover's algorithm, although may be not the most effective way of quantum computing, but it is also one of the most popular approaches of quantum computing. However, I should mention that this 1994 work of Shor is by far the most complete application of quantum computing and also is one of the most important basis of cryptography. Some of the applications today that is being already done in defense labs in some of the countries around the world is due to the fact that this factorization to give rise to this extreme security is possible because of this particular principle of Shor's algorithm, which gives rise to exponential speed up. Okay. Now, the basic idea of qubit is that the case where the quantum system with exactly 2 degrees of freedom. Okay. Now, let me also point out that I am giving you the picture which is an evolved picture. In the 1980s, people were not really concerned about just the 2 degrees of freedom. When the first idea came and the ideas of superposition and entanglement became clear, people wanted to use many degrees of freedom. But soon it turned out that in order to maintain the language which can be continuous between the computer scientists as well as the rest of the community developing this. So, this has a lot of people in this area. So, QC essentially is represented in one side by computer scientists, mathematicians, and on the other side by mostly physicists and some very odd people who are interested in physics. For example, Seth Lloyd, he is a mechanical engineer. So, all of these different people who have an inclination of physics understanding or interest in physics have also contributed hugely in this. But in order to make sure that the community understands each other quite well, more to say that the computer scientists are finally able to use and make it or compare it with the classical computing, it was decided that the 2 degrees of freedom should be the benchmark, because classical computers essentially still realize this based on that binary principle. So, we will be using the same principle to go between 0 and 1. I mentioned this right away here because there is a large, and we will perhaps look at it in some point or the other, there is a large number of body of work which has also parallelly developed into having multiple states or multiple degrees utilized for quantum computing. Very often those are known as qudits. Okay. Anything more than 2 when it goes, it is called qudit. That is a typical area of development which has also happened, and people have shown that you could use qudits to do computing without any problem. It is like saying if you have, it is like having a decimal system versus a binary system and so on and so forth. You can have more than just 2. So, just to clarify. Now, once you say 2 degrees of freedom, then there are some very common ones to look at. One is, say for example, the hydrogen atom, ground and the excited state. These are the quantum states, spin half system, and that can be an electron, positron, nuclei, any of these would work, right. So, that is the situations. The state of the qubit is generally, as we mentioned, superposition of 2 basis states. So, here the starting point is our basis states. So, that is coming from quantum mechanics. We have been looking at the basics of quantum mechanics before. So, we already know that everything starts off with basis states, and here we are basically confining ourselves to the 2 basis states that we start off with. The rest state and the excited state are the basis states of hydrogen atom, for example. Rest or initial, the ground, it can be anything. For example, again in the spin case, the spin up and spin down are the states that are basis states of the spin half electron. Now, based on these, you can have the vector picture which we discussed, which is essentially the idea of Dirac, and he used this bracket notation, essentially representing the arrow going one way versus the other, and very effectively using this pictorial principles to develop the entire shorthand math associated with this entire process. The reason for Dirac to develop this was he was the first one to do the entire relativistic quantum mechanics, and with the help of using relativistic quantum mechanics he was able to for the first time show the spin quantum number to appear and not ad hoc put in as was done in the non-relativistic scheme. So, those of you who have done relativistic quantum mechanics, you already know what I am talking about. So, for relativistic quantum mechanics, this was critical to be able to develop the ideas of shorthand notation. So, it was important to develop the shorthand notations to take care of the entire math that was going to go ahead with it. Simply put, it is a much easier way of looking at the entire problem. There are certain notions that you go by doing this. One is to say that the basis states for each qubit can be written as 0 and 1 for instance, and then each of them is associated with some probability or some amplitude factor. And they can be all complex. So, for example, alpha and beta, as long as the square of them add up to 1, you are allowed to take any complex number for them. So, that is how you bring in quantum mechanics. So, at the very beginning, whoever is entering this field, for them it is important to notice the main difference between a classical system versus a quantum system. Even here, in terms of writing out the linear way of writing everything out, is the fact that we invoke complex numbers for the amplitudes. Okay. And so, these numbers by themselves really have no physical understanding, no physical meaning. Only when you square them, then they start having some meaning. Okay. So, you get the feeling as to how probability is associated with the square and not just the amplitudes. So, we can use any kind of basis sets. Instead of 0 and 1, we can use any other one, as long as we can distinguish them. The basis states are typically chosen in terms of orthogonal vectors. The reason being, the inner product of the two vectors then are determined or are confirmed to be always 0 when you take orthogonal, right. This is always going to work. So, you set up the problem this way. So, you could also use say plus minus notations for this, and you can go from one basis set to the other. This is basis set transforms, again something which you have done quantum mechanically many times. For simple cases, it is just a rotation. For instance, here we are showing an example of a 45-degree rotation from the original orthogonal states of 1 and 0 to plus and minus, which are off by 45 degrees, and you can just easily rotate one to get to the other. Okay. So, this is a qubit rotation in some sense. So, this in itself, whenever you look at an answer or situation like this, you are going to visualize what it means. So, here is our first example of an operation. Why is it important? Because these are the operations that form the basis of how you are going to develop your computer. So, just this very simple idea that you can actually rotate a basis set gives you the first principal idea of an operation in a quantum sense. Now, when you have more than one qubit, then their internal rearrangement gives rise to many more conditions. So, for instance, if we know the individual states of electrons of a system given below, so these are 3 electrons, let us say, their individual representation on the basis of how they are would give rise to the 3 different possibilities of representing them. right. So, I could always write my different wave functions psi 1, psi 2, psi 3 with amplitude factors in such a way that will give me rise to 3 different wave functions. They can be as simple as 0 and 1 amplitudes, which give rise to either one or the other state as it is being represented here, or it could be much more complex. So, if we write it like this very simply and we ask the question what is the overall state of the 3 particle system, then we will be able to look at their composite products as their solution. Okay. And these composite products are tensor products, they are not anything else but tensor products. So, this is again a definition here. So, the inner product was the term where we used the basis sets to tell that they were orthogonal, right. So, 0 and 1 when they form the orthogonal set, their inner product was 0. But when I actually take an outer product which is representing the final state of all these different qubits that I have taken, that is my outer product. And so, this is, so my final state psi is essentially an outer product of all these 3 different states that I have, which is a tensor product, and that gives rise to the state. And so, this is very different from the inner product. For any 2 states, if I take an inner product, that is not going to be the same as the outer product. So, if I want to write, if I take the phi and psi for instance, if I want to write this is my inner product as I have mentioned here, then the outer product will essentially be phi and psi. This is my representation which corresponds to right. That is what it means. So, the tensor products are written in this way. I could also as well represent this psi 1, psi 2, psi 3. So, this is the shorthand notation which goes outer product, inner product, and this is how they go. Okay. Now, in this particular case where this was just set it up like this, we will finally find that my state psi is going to be just represented by a state which is 101, which is a tensor product of the states corresponding to each of them. Okay. Now, that is how you represent states. The next important thing which we would like to understand is the concept of gates. So, the first thing we discussed was qubits. First thing is quantum mechanics and classical mechanics, concept of computer, the very basics of it. These are how we build. Then we looked at what is a qubit, we defined qubits, and we specifically mentioned the way we are going. Then we came to a point where we looked at the way the qubits are defined in terms of when you have multiple of them, and then it is also looked at to say whether we are going to take inner products and outer products, what do they mean. Inner products typically are projections, outer products are basically the final state, okay, when you have multiple of them, and that is what we looked at. Now, when we are going to see what can you do with them, that is when we are going to do the quantum gates. Now, it can be parallel to the idea of a classical gate. In terms of the classical computing, a gate is an operation on a unit of data where in our particular case it is a qubit in this particular case, right. A quantum gate is represented by a matrix that may be applied to a state vector. Now, you can already see why it is a matrix, because we are now looking at states which were being represented has vectors which are also essentially single order matrices. So, if you want to operate on them and change to another one, you need a matrix, most often the square matrices. So, quantum gates are essentially often square matrices which can give rise to the vectors changing into the states that you would like. Now, we will talk about this in more detail later, but for now let us look at some of the examples of commonly used gates. Now, this is important here. So, let us start with some of the gates here. One of them is called the Hadamard Gate, and they are represented by different notations. Unfortunately, the Hadamard Gate representation is H, which is very close to an Hamiltonian. Therefore, please note, for this class we will be using the Hamiltonian in a cursory manner. Okay. So, this will represent Hamiltonian because we are used to using Hamiltonian for generating energy, whereas for the Hadamard gate we will be using the H, regular H, capital H. Then there are these very important Pauli gates. So, what are these Pauli gates? Okay. So, I will come to them. The next one is the Pauli gate, which is also very important, and the first gate which is of consequence to an actual computing is the control NOT gate. Okay. So, we will go by them quickly to understand how this goes. So, as an example for the classical case, so this is a parallel that we are building, the simplest Boolean gate is NOT. So, for the simplest case of a single qubit, what is it? We put in one case and we get out the opposite of that. It is a NOT gate. Whatever you put in, the opposite comes out. So, if you go up, it will come out as down, and so on and so forth. So, 0 1 goes in and you get an 1 0. Now, one of the very important things to remember is that in quantum gates, however, you have to define it not only on the basis of the equivalence of 0 and 1, but also on the basis of their superpositions. Now, this is one very important point that you have to remember. Just by looking at the final outcome, which is the classical case, you could have done or made your gates, but in quantum mechanics that is not just the case. Every other possible superpositions also coming from the same condition should also be following this rule. So, that is the idea. So, here is an example. You have a state 0 and you have a state 1. So, if you want to define a NOT gate, what you would want to do is you want to have, say, NOT operating on 0, it should give 1, and NOT operating on 1 should give 0. Okay, that is what you expect. So, the action of quantum NOT gate on a superposition must then also have a situation where if I do this, then it should work, which means that this very important point is going to be always maintained in case of quantum mechanics, that all the quantum operations are going to be linear. Okay. So, this linearity, now it should not come to you as a surprise, because you know that when we did quantum mechanics or when we have been learning quantum mechanics, we have always mentioned that quantum mechanics is always going to work in a linear way. All the operations in quantum mechanics are linear. The allowed operations, or the ones which you actually call are measurable operations, are always linear. So, whenever you use a Hamiltonian, the Hamiltonian is linear. Whenever you use a momentum operator, the momentum operator is linear. The position operator, it is a linear. Okay. So, that is the point, that if it works for any particular set, then all the superposition states also should be following that, which means that a requirement of quantum operations are that they are going to be linear. Now, how do you get that? So, this is the logic behind why do you have a matrix for a quantum gate. The logic being that the quantum operations have to be linear, right. So, we can represent the action of a quantum gate by a matrix. So, the quantum NOT gate, or it is also known as the Pauli X gate, is written by this form. The X is equal to a matrix which is 0 1 0 1 0. This one whenever you operate. So, here is the way how it works. The quantum state is represented by a vector. So, 0 is 1 0 whereas 1 is 0 1, and the any psi which is a linear combination of these two can be written in this form. So, you can now express, we can now express the NOT operation as a on a generalized qubit by using a matrix manipulation method, and you will find that this always works. So, that is why your NOT operator X is working properly as a quantum gate. Okay. And you can immediately see that NOT was a good one to take, because NOT is one of the classical gates which is reversible. So, I specifically chose the one to start with which is a reversible one. It makes sense, everything goes well. So, let us look at another important single qubit gate. So, this was a single qubit gate because we just used one qubit. The other single qubit gates which are important, that was the Pauli X gate, and this works on one qubit. The other common single qubit gates are the Pauli Z gate. So, the representation therefore would then be in terms like similar to the way that you write the classical ones. You will be writing out how they are. Pauli Z gate is 0 1 0 0 minus 1. Then Pauli Y gate is a multiplication of the Z and the X, and the Hadamard gate is essentially a square root of the NOT gate. Okay. So, you can for your own you can do these small little exercises to prove it to you that this is how they work. So, if you just apply Y, what does the Y look like, you should write it out. Similarly, the Z is anyway given, but the fact that the Hadamard gate can be actually written in this form by taking a square root of NOT is just simple exercise. You should just refresh your matrix manipulations by doing these things. Okay. Now, the summary of the simple gates therefore are these X gates, basically the NOT gate, alpha 1 0 converts to 1, beta 1 converts to 0. Then the Y gate, which basically is a complex conversion. It has a part which takes you like this, and then the Z gate gives you that, finally the Hadamard gate. Now, this Hadamard gate is actually very important as we will find out later, because what it is producing is a superposition of the two states that are involved with the individual amplitudes, right. So, basically you are sort of equalizing the two states, right. I mean, if I take a if I take my basis now to be 0 and 1, superposition of 0 and 1, any one of them, then I will get a 50-50 combination of them. So, that is the reason why it becomes useful. Now, the reversibility requirement is, we have been doing that, but now this is the point where we should look at it. Since all the quantum operations have to be reversible, we have this principle that our gates have to be designed in a particular way so that they are always reversible. This is not true for the classical case, and that is what is written in the next time, which is that Boolean operations are not necessarily reversible. A reversible operation is always given by a unitary matrix for which, so all our quantum gates will be written, will be possible to be written in terms of this kind of a unitary transforms. So, that is one other point which we have, that any gate that we devise will have a unitary transform. So, it will be possible to get this inversion very easily. Okay. So, any operation that you have its inverse available, right. So, that is the advantage of it. So, now let us look at the Hadamard gate, because it is an important gate, and as I said, it places it in a superposition of 1 and 0. So, this is a gate which takes one qubit and puts it in a superposition state of its own two states. So, this is important because you will find many practical uses of this Hadamard gate later on, and this is the representation that you will. So, in shorthand notation, when you write circuits which is analogous to computer circuits, you will be having this kind of scenario where you will be feeding in the states and you will be having an output state like this with just the circuit diagram given like that. So, you should be able to interpret these kinds of simple circuit diagrams to you. That is one of the learnings that we do in this, because we will be soon going to cases where I will be simply showing you pictures like this and we will not be writing down these other steps. If I give you this, then you should be immediately able to recognize that this is how it is. Or if I just give you this, then you should be able to understand how this is happening. This is important because this is a language that we will be following for building up quantum circuits. So, the Hadamard gate, for instance, can give you very interesting results. So, with 0 as an input, you will be getting a superposition of the sum. With 1, you will get the superposition of the difference. When you put in the superposition state in there, you would actually get a superposition of the individual components with equal probabilities of theirs. Okay? Or another way of writing is this one where we are actually taking. So, in some sense this is a very important gate for basis transform. This is very important because in quantum mechanics it is all about taking the problem to a basis where it is easy. That is the reason why quantum computing is also going to take advantage of that. And the design of a quantum algorithm or anything else that you can think of is 90% relying on this idea as to how smoothly can you come up with ideas with which you can do your basis transform to a condition where it is the easiest to solve the problem, and then you come back to the states or the transform back to the case where you were, so that you can get your result. Okay. That is the point of this entire place. So, Hadamard is almost 99.9% you will always find a Hadamard gate existing in any computing. You cannot avoid it because you always need to do basis transforms. That is one thing. Similarly, if you input this superposition, you will get back 1. So, this is basically complementary. So, it shows that it is a completely reversible condition. So, if you believe in this, then you can immediately get the other, and so on and so forth. The other important gate is the Pauli gate. Once again, it is important because the Pauli gate is important for phase shift, which means that the phase of the two states can be reversed. For example, this is their 0 and 1 are in the same direction, sum, but the reversal will make 1 is plus and 1 is minus. So, this is a phase shift, whereas the sigma x is a bit flip. So, we started off by saying these were the z, x and y gates. More formally, in terms of the Pauli gates, they are more known as the sigma z, sigma x and sigma y, and to complete the identity goes along with it. So, these are our final set of 4 Pauli gates, and these are very important in terms of anything to do with spin. Okay. So, that is the part which is very important about these Pauli gates. So, one of them, so you can see this and understand that z is only one dimension z, sigma z, that is only phase shift. If you do a bit flip, that is along the x axis. If you do both phase shift and bit flip, which means that you are doing y, which is a composite of Z and X, you will find this, and the identity does not do anything, but this is necessary to complete the gate set. So, that is what the Pauli gates are. Now, these are the corresponding Pauli matrices. They are also often written as 0, 1, 2 and 3. 0 is nothing but the identity, sigma 0, then sigma 1 is the X, sigma 2 is the Y, and sigma 3 is the Z. I have given you all the different notations which are used in different books. Okay. Each book uses different notation, and to be clear, I have put them all in this particular slide so that there is no confusion. Wherever you see these, you know. These are the most popular single qubit gates, right. Okay. Now, the final, the first gate which we will do, which is more than the single qubit gate, is the control NOT gate. This is a 2 qubit gate. Okay. So, why you need more than one in this case is because you need a bit for the control. Okay. So, it is more often known as the so this is our other bit requirement. So, the control NOT gate or the CNOT gate, as it is popularly known, is a standard 2 qubit quantum gate, and it is defined in this fashion. When you are only operating on the 0 0, then it is just going to give back the same one, because your control parameter is essentially the 0. So, whenever you have zeros, then it is leaving it. So, your operation and the control essentially gives rise to what is going to happen. So, the 1 flips the bit and the 0 is no change. So, that is your control. The first bit is your control, that is working on the other one to do the NOT, right. So, that is why it is a control NOT. So, the state of the first, if it is going to be 1, will give rise to a flip. If it is going to be 0, it will not make any changes, right. So, that is why it is a control. The first bit decides as to whether it will act like a NOT gate or not. So, that is why it is a control NOT. So, it has a notation, this is its notation, a plus with a 0 inside the 0 there is a plus. So, it is a generalization of the XOR, classical XOR. Okay. If you, or they call it XOR, XOR, whatever way you want to call it. So, the classical XOR is essentially this, where you have this principle, and here you are using this 2 qubit case, where the second bit is going to behave based on what the first bit is going to be. It is drawn in this fashion. This is also important to know, because you would like to see it. So, basically the first bit remains as it is. So, whether it is 0 or 1 remains as it is. The second one is going to change, and depending on whether the control is going to do something or not, it is going to show up as a result. That is how it is. So, the first, so obviously if it is a 2 qubit gate, then it has to be a 4 by 4 matrix, because for the 1 qubit gates we were using 2 by 2 matrices. So, this is a 2 qubit gate, this will be a 4 by 4 matrix. So, the simplest matrix corresponding to the CNOT will therefore be this. So, here you can see that this is my CNOT gate, and here is an example of applying the CNOT gate for a matrix which is Y, for a state which is Y, and you get the solution. Now, this CNOT gate along with the single qubit gates are universal for quantum computing. Okay. Irrespective of how you formulate your problem, these will be always a complete closed set. Okay. As you go and make bigger gates, they can often be broken down into these basic gates. But these gates cannot be broken down further. So that's what it's known that if you can go to the very basic states, that's how they are. Okay. So how can you actually use them? So the first important thing about the quantum computing is that once you have learnt your qubits and you have learned some operations which are your gates, then you can actually write out your circuits. So we have been doing that, but here is the basic principle of how to go about doing something which is a combination of more than one applied gates to get to where you want to. So, for example, we would like to just show a quantum swap circuit. So, I would like to go from A to B and B to A. Okay. So, the point is if you apply only one gate, it will not be possible to swap both. As a CNOT will only swap one of them and the other one remains constant. But if you apply it twice, then you will end up producing a swap gate, a quantum swap circuit. So, this is exactly an example of that. So, by using just control knots in series, you will be able to get this happen, right. So, you can actually start building your interesting circuits right from this very basics that we have just learned. Okay. So, this is a circuit, let us see. So, here is the point that is being shown step by step. So, what does the first one do? First one generates a CNOT, so you get this. Next one, you have not applied anything on this part, so it is only going to be the next. And then the second one is going to be this, which is going to go to become B, and then that one again remains same, whereas the other one finally goes and applies this one to get back the A. So, how many CNOTs did I use? 1, 2, and then the third one. Now, if you tell somebody who does classical computing, he will just look at you and say, come on, you just swapped qubits, you swapped 2 bits. For that you have gone through 3 3 controls and 3 gates to do this. But one very important thing to note here, however, is that this is reversible. I can as well come from this side and I will have the same result. That is not true when you do a classical computing. In classical computing, yes, you can actually swap them just like that, but you are expending energy. You want to go the other way around, it is expending energy because it is not reversible, it is not the same way how it works. Okay. So, that is the idea. So, that brings it to a very important point. What are the basic features that we are now looking for in a quantum circuit? We cannot do a few things that we have just now realized. No loops are allowed. Okay. Quantum circuits are acyclic. You know why? Okay. So, there are no loops which are allowed. So, quantum circuits are acyclic because you cannot parallelize loop circuits. Even when you do parallel processing in a classical computer, the most difficult part is the nested loops. So, generally speaking, you are not really supposed to have nested loops if you are trying to do parallel processing. So, for example, fan in, you can understand that why fan in is not allowed. You are going to lose qubits, you can't have that. And similarly, you cannot gain qubits, so you cannot have fan out. What we are going to do is that we are going to take on more from this point on into the further lectures. For today, let us stop here and we will continue on with this in the next lecture. Thank you.